Welcome back. We are still on logarithmic functions, and on this lecture or on this video presentation, what we're going to do is to graph some of the functions commonly identified as the logarithmic functions, and also we are going to define what their domains are. So the first function that we're going to tackle is f of x is equal to 3 log x minus 1. So first of all, we are going to define some points for us to be able to determine the behavior of the graph. And notice that logarithmic functions are pretty much the inverse or the inverses of the exponential functions. So for now, we already have some idea. Since exponential functions normally behave in a trend that goes on from a certain asymptotic behavior. So in this case, let us say this is y is equal to 2 raised to x. Okay, and this function passes through here or crosses the x-axis at the y-intercept when x is 0, so y is 1. So this is 0, 1. And it remains asymptotic on this portion because it will try to reach our x-axis, our negative x-axis in this case, but it won't be able to touch it. So therefore, it has an asymptote at this portion. So x-axis, or when y is equal to 0. Okay? So when we have a certain reflection or a certain function also, which is called y is equal to x. Now, this is the, what do you call this? This is the line of reflection of both the exponential function and the logarithmic function. Then this portion here, which is an x-intercept of 1 and 0, will become the defining point now in observing the behavior of this logarithmic function as the inverse of your exponential function y is equal to 2 raised to x. And this will be the trend in the behavior. So you can notice that they are reflections of each other. And this graph now is trying to reach our negative y-axis, because once it gets there at negative infinity, it will try to reach 0, but it won't be able to touch it. So this function here is the inverse of this function, and this function will be log 2x. Okay, so now let us tackle on our f of x is equal to log of x minus 1 by giving the impression of the parent function. So what is the parent function in this case? So we are done with this illustration here. We can now erase it. So let us start everything by getting the parent function of our function, logarithmic function given for a. The parent function of our letter a is log x, right? And that's the parent function. That's the most basic function for all of the logarithmic functions. So f of x is equal to log of x. Now, suppose this is my column for x, and this is my column for y, the other side, okay? So if this is my column for y, then if my x's are, of course, we can have 0, 1, 2, 3, 4, 5. So the value of my y, okay, for instance, you have to press on the log function there. Okay, in your calculator, you have the certain log expression. Okay, just press on the log of 0. Of course, log of 0 does not exist because, so this does not exist because log is just an inverse of your exponential function, and we could see that for exponential function, the parent function of an exponential function, which is f of x, is equal to 10 raised to x in this case, because we have a base 10 here, then we have an asymptote at the x-axis, or when y is equal to 0, then we don't have a value for x. Okay? So if we press on log 1, that gives us 0. Okay? A log 2, that gives us, what is our log 2? So log 2 gives us 0.301. Okay? And log 4, so log 3 gives us 0.477. So notice that the log values are increasing, okay, from 1 forward. So log 4 would give us 0.602. And log 5, the last of the examples of x values that we get is 0.6989. Okay. So suppose this is our x-axis. So this represents the x-axis, and this represents the y-axis. And this is the origin. This is 1, 2, 3, 4, 5. And this is, let's say this is 1, 2, 3, 4, 5. So let's say this is 1. Okay? And 1, 2, 3, 4, 5. This is 2 here. Okay? So when we have 0, it does not exist. So clearly we have an asymptote at y is equal, or at x is equal to 0, or the y-axis. If our x is 1, then we have an intercept. So we have an intercept here at x is equal to 1. And then 2 is 0.301. So this is divided into 5. 1, 2, 3, 4, 5. So this is 0.2, 0.4, 0.6, 0.8, 1.0. So 0.301 should be somewhere here. Okay? And we have, let's make it more accurate. We have here. And then 0.477, so somewhere here. Okay? And then 0.602, so that would be here. Okay? And then 0.6989, so that would be here. Okay, now tracing the parts or the points there, we can now create a curve defining our log of x. So this will be our log of x. So it should be like that. And this one will be like that. It won't touch the x-axis. So that is our parent function. So f of x is log of x. Okay? So what about our f of x is equal to 3 log x minus 1? So this case is an example of as you could see it, we have a vertical dilation 3 units up, or a vertical dilation of 3. So this function here, the parent function here, is dilated by, so we have a vertical dilation by a factor of 3. Okay? Vertical dilation by 3. What else can you see there? There is a horizontal translation. Horizontal translation by 1 unit to the right. So this means that we are going to move our asymptote 1 unit to the right. Okay? Translation 1 unit right. Okay. So this means that we are going to translate our parent function f of x is equal to log x 1 unit to the right and dilate it by a factor of 3. So I have prepared the graph here, and And this graph shows you that indeed our x-intercept, look at our x-intercept here. I should choose a lighter version. So look at our x-intercept here. It is already translated 1 unit to the right. So our x-intercept is translated now to 2. So from 1 it became 2, right? So from here it was translated to x is equal to 2. Okay, so that means that the function itself could just be taken from the parent function, because parent functions are more commonly or more ideally graphed, okay, without the use of any calculator. So without the aid of a calculator or going through complex terms in logarithm, like in this case we got 3 log x minus 1, then we could just rely on our parent function, and from there we could do the translations or transformations. In this case, we translated it 1 unit to the right, at the same time dilating it by a factor of 3. Okay, so that means that we are raising. Okay, we're raising the we are stretching technically our function log of x. So this is our graph for f of x is equal to a 3 log of x minus 1. Now we go to letter B. F of x is equal to negative ln of x plus 3. So f of x is equal to negative ln x plus 3. So again, we begin with the parent function, and the parent function of this function, given function, f of x is equal to negative ln of x plus 3, will be f of x is equal to ln of x. So our parent function is f of x is equal to ln of x. Now let us investigate our ln of x. What is the behavior of our ln of x? And we have specific values of x and determining our f of x. So if our x is 0, so that gives us ln of 0. And ln of 0 is the same as a while ago. It is also undefined. Okay, so it does not exist. Therefore, we have an asymptote at this point, at x is equal to 0. So where is x is equal to 0? Just the y-axis. Okay, this is our x-axis. And if x is 1, then ln of 1 is 0. If we have x is 2, then ln of 2 is equal to 0.6931. 0.6931. If x is 3, then ln 3 is equal to 1.0986. If x is equal to 4, that gives us ln of 4, and that will be 1.3863. And finally, if we have 5, then ln of 5 is equal to 1.0 or 1.6094. And notice that our y values increases also. Our y values increase from 1 to infinity. Therefore, having defined the values in the domain of our x, chosen domains from 0 to 5, then we could now plot our parent function f of x is equal to ln of x. So we have undefined the value when x is equal to 0, and we have 0 when x is 1, so it's here. And we have 2, if x is 2, then it's 0.6931. So again, we would have to define these units are scaled 1 unit from the origin. so 1 unit from each other also. And this would be, so we are going to divide this into 0.2 for each unit. Okay, now we have x is 1 and y is 0, x is 2 and 0.9693, so it's like 0.7, so it would be here, and 3 1.0986, so it would be something like 1.1. Okay, so it's here 1.3863 for x is equal to 4, so it would be here. Okay, and for 5, x is equal to 1.6094, so it would be here. Okay, and now we are actually graphing the we have to connect all of the given points here, so we would form a curve that looks like this. Okay, so this is our, okay, I want to have a smooth curve, so I'm going to start it from here. Okay, so this would be my ln of x. This is my parent function. F of x is equal to ln of x, or y is equal to ln of x. Now in the given, we have to get f of x is equal to negative ln x plus 3. So first, what do we get? First, we notice that we have a horizontal translation. So horizontal translation of 3 units left, right? 3 units left. Okay. What else? We have a vertical dilation. A vertical dilation or shrink. A vertical shrink by -1. So it is indeed, and this is another observation, that it would have this function, negative ln of x plus 3, is a reflection, a vertical reflection across the y-axis because of the -1, the dilation of -1. So we reflect it across the y-axis at the same time. At the same time, we translated 3 units left. So here is what the equation or what the function would look like. Okay, so I'm going to try this. I prepared the graph already. So this is the graph, and I'm going to rearrange this for you. Okay, so this is what f of x is equal to negative ln of x plus 3 would look like. So this is f of x is equal to negative ln of x plus 3. Okay, it is a reflection, and it has an asymptote at x is equal to -3, and as you can see here, as compared here, now this graph is an asymptote when at the y-axis, or when x is equal to 0, right? And in here, since we reflected it across the x-axis, then this asymptote here is x is equal to -3. Okay, since it is translated 3 units left. And of course, the intercept will also change, and this intercept here will be translated 3 units to the left. So this is x is equal to -2. Okay, so this portion here is negative 2, 0. Okay? So this is the answer for letter B. F of x is equal to negative ln of x plus 3. Now let us graph log of 2 x squared minus 1. And to graph this, we need the change of base property for logarithmic functions. But before anything else, we are going to end on this video, on this lecture, and we're going to continue this on the next presentation. So thank you for watching.